Okay, on this lecture we're going to look at errors when you calculate things and also when you are measuring things. There are errors can be occurred. So we get a little awareness how the errors occur and what is the purpose and what is the reason for this can happen, especially in electronics. So that's what we're going to look at. And here in this book they're talking about some of the errors listed here just as an examples. If you see the sensor measuring barometric pressure might malfunction. What is barometric pressure? That is actually you measuring the air pressure on the atmosphere. That is what this device does, and this pressure is always changing. We know in the sea level it is, I think, 14.7 pounds per square inch, the PSI value. And yeah, if that malfunctions or if it is not giving you the accurate data, the whole weather system can be collapsed or not going to give you accurate data in it. So yeah, it's highly likely it can go wrong. I'll be looking into the electronics in next few slides and see why and what is the reason you would say the data having more errors. Okay, so the giving incorrect values and the values that is not in the right range, that can be happen in some devices. That this is something related to overflow and underflow matters. We'll look at that as well. The accuracy of a sensor might not sufficient enough, so that means the calculations are not handling into the depth. So that is when it comes to floating point operations, we're going to look at that. The fail to calibrate instruments. So this is something like let's say you are measuring your weight on the weight scaler device, right? So we used to have old scaler devices like this, and let's say you have your measure which is starting at exactly 0, right? Then whenever you get onto this, it will go and show some value. But what if it is not exactly on the 0 at the start? Let's say you have right here, this is your starting position. So in that case, there is a little gap between 0 and that. Well, I have seen this in many the old scale devices. It is not calibrated right, or you have not starting on the right value. So that is something that you need the collaboration, especially when it comes to that, right? Misreading measures means yeah, you measure your weight somewhere here and you don't want to be that value, so your mind says a little bit lower and things like that, or you visualize, you see something is not accurate, things like that, but yeah, that can be a human error actually, the misreading. More than the system, it can be a human error, but in the systems also it will get a wrong error measurements. It can be happen, right? Recording results in directory, this part is one part of this one related to this, of course, right? So those are the things that can happen when you're collecting data and analyze those. There are more errors that we're going to look at in this this lesson about errors. Okay, so right, so before I move forward, I'd like to address few things. So this is for the make error in a formulation model. So that means simplifying assumptions or determine the incorrect equations can cause a problem, right? So this is actually the human error, right? We missing the crucial factors of your modeling, or if you are not making the right assumptions, or you determines the incorrect equations. Of course, there are so many things can happen. Okay, especially when you come to the rate of change. If your rate is wrong, well, that causes you a lot of problems in your modeling. So you might not get the exact value as you expected, right? And implementation is the computer program implementation model. Computational scientists can make the logical errors. That's one thing, right? So, and also the different unit measures like the centimeters and meters, you suddenly apply pounds and other equation measurements, so it can also cause a problem. So that is something that you have to keep in mind when it comes to actual calculations, right? So before I come here, let me address one thing when it comes to the computers. So let's see how the computer is made of before I move on to the next level. So well, the computers are made of actually switches. So the switch is what? So it's just a normal switch that you have at your home. It can turn on things and you can turn off things, right? So actually using the current, that's all you can do. There are no much things that you can do with the switch, right? So using this concept, you come up with some set of switches. So these are the switches in a computer, right? So usually you will have 32 switches like that, right? 32 of them like this. Okay, we call this a register. So this is a register, right? So if you have 32 of them, that is a 32-bit machine. So these kind of registers, you have some number of registers in your machine, and this is where you're going to store your data, right? And access data. So how you going to store your data is either this switch is on and off, right? If it is on, it says it's 1. If it is off, it is 0, right? So like that, you have possibilities to set up your register, right? One or the other. So this is how you store numbers. This is how you store any data in a computer, which is nothing but a switch which is turning on and off, right? And it can store a value. So for example, if I say 5, number 5, I want to store in the computer, right? So what you do is actually you convert this to a binary number, which means I have only two possibilities, either on or off, right? So in this case, converting this one to binaries, you divide this by 2. You divide this by 2. So then when you divide it by 2, of course 2 multiplied by 2 is 4, right? So I can have 2 and remainder is 1, right? Again, if I divide this by another 2, I get answer 1, remainder is 0, right? So you see, now I convert this 5 into zeros and ones, right? Then what you do, you're going to write it right here. So this is how you're going to store number 5 into the computer. Okay, so these are switches. If this means this switch is on, this switch is off, and this one is on. So in that case, you have number 5 in your system, right? How do I convert it to an actual number? Well, usually this one is called 2 to the power 0 position. We call this one 2 to the power 1 position, and then we call this one 2 to the power 2 position, right? So if you want to convert this to the decimal number, so this is a binary number, so this is called binary number. Okay, so this is binary, right? If I want to convert this binary again back to decimal, or the decimal number, what you do is you multiply these two together, and you multiply these two together, you multiply these two together, and add the answer. So in that case, if I multiply these two, 2 to the power 0 is usually 1, multiplied by 1 is 1, right? And then plus this 2 to the power 1 is, the value is 2, multiplied by 0 is 0, and 2 to the power 2 is 4, multiplied by 1 is 4, right? So this answer here is 5. So that is how you get it back. This is how we store it, this is how we get it back. Okay, so any number in whenever you want to store it, this is the way you can store. Right, so it's starting from 2 to the power 0. So the maximum number you can store in this one is 1 1 1 1, like that. So you can store the maximum number of 32-bit register is nothing but everything is 1, right? Yeah. So what is the actual value here? Well, that means 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus like that. So is the addition of all, right? So that is actually, when it's come to at the end, this will be equal to 2 to the power 31, right? So that is actual value is going to be, right? Yeah, so that is the total number that you can have by adding everything together. Okay, so for example, if I have only 3 cells, that means I can have one here, and one here, right? So this is the addition of, this is 1, and this is, if you multiply these two, you get 1 2 here, right? And so the total here you get nothing but 7, right? Okay, so nothing but 7, that's what you get there, right? So well, the same way, that is what, 2 to the power 8 minus 1 is 7, right? So like that, I'm sorry, you can have actually this is the maximum number you can store if you have 32 bits, like that. If you have 3 bits, it's 2 to the power 3 minus 1. So if you have another value here, that will give me 2 to the power, actually you can say 2 to the power 4 minus 1, right? So you can get that value, which is 15, right? So each time it will get number of cells that you have. If you put all these ones, then the answer will be the total 1 minus 1. So if you have 32, it is 2 to the power 32 minus 1. That is the answer is going to be. That's the maximum number that you can store in number of bits, right? So in that case, what happens if I have 4-bit register, which is only 4 switches I have in my machine, and I want to store something big like 20. Well, there's no way to do that in one register, right? So if you fill all by 1, right, you get the maximum is 16 or 15 in this case, right? So well, if it is 15, how can I store 20? Well, that is a problem, right? So anyway, this is what the limitations the computer has. So there are some software solutions. Of course, you can use the 2 registers instead of 1 and handling things separately. But only difference from the early days computer to today is today's computer has smaller size registers. Long ago, when it comes to the first computer, it will be size of a building. Why? Because you have huge switches like the ones you have at home, right? So it is always a big one, right? So by the technology improves, so you can have this in your handheld devices. All the switches in there is very small now, right? So but the mechanism or the idea of storing data in a computer is the same. So it is only the on off switches you have, and this is how you do it, right? So that is a fact for up to now. Any computer still following the same rule and the idea of storing values. Okay, right? So let's talk about something interesting. How can I store a floating point number? So what are the floating point numbers? Well, whenever you go shopping, right, or somewhere to buy a computer, you may heard the word flops, right? Flops. Right. So what does this word flops means? Floating point operations per second. So that is what flops. There's no a here, right? Floating point operations per second. Okay. FL is operations piece per second, right? So that is what the floating point operations per second. Why is it significantly important, right? So this is the hardest operation a computer can do. Why? Because whenever you say a floating point number, I have a dot in there, right? So there's a dot here. Well, I just said you have only the switch like this, right? These are the switches you have, and the switch can represent only on and off. So how in the world I can get a dot in there, right? So that is an interesting question. And well, in mathematics they represent this one using different way of representation and number, right? So this is what we call we talking about here in this this line right here. Okay, so how do I represent a floating point number in a register is the question, right? So the best thing I can do is, right, I can get a number. Let's say this is my number that I want to store in my computer. So you can write this separately, differently. Like how do you write this is equal to 0.956 multiplied by 10 to the power 1, right? I just move this dot here and I'll say, okay, so if you multiply this by 10 to the power 1, you get the answer, right? So like that, if I have another one which is 2 to 2.5, and if I want to represent in this form, I can put it 0.225 multiplied by 10 to the power, right, 10 to the power 3, like that. So so this, if you write it in this form, right, there are important things that I have to consider. One part is this value right here, right? The other part is this value right here. Okay, so I can actually separate these like that, or represent this number in this form, and then take this value and store, and then take this value and store in the one register. So I divide my register into pieces now. So one piece of that will represent this number, and one piece of that will represent this number. Right. If it is a plus or minus, that will come here. Right. So this is actually a binary form. You have to convert this to ones and zeros. You have to convert this to minus ones and zeros. But you can have this structure to store floating point numbers. So you can see it is a hard process, which is just not like numbers. Now I have to consider these dots. In that case, I have to convert this one to some form look like this, and then you store these values and these values. So that's how you represent floating point numbers in a register, especially in a computer any type. So because of this reason, it is the hardest operation the computer can handle, right? So that's the reason you say, okay, the flops are, if you can execute number of flops in your machine, that the high number of flops, that means you have a pretty powerful machine. Otherwise it will be slow. So the flops calculation is important when you are looking for a performance in your computer. Okay, so that is the fact. And next time when you go and try to buy a machine, see how many flops it can execute, right? Right, so the floating point numbers to be printed in exponential form. So this is exponential form actually. So you may have seen this in your calculator. It has a little e in here, and then a number. Right, so this is exponential form. This is not normalized, so you can see the dot is on in front of dot, there's a number here, right? But when you store it in a computer, you actually don't have this dot here, it will be somewhere here, right? So this means what? This means you have 9.843600 multiplied by 10 to the power 2, obviously, right? So that is what it means. So this means actually you can write it differently. When you're having 100 here, actually it is 984.36. you don't consider these zeros, so this is the number actually. And if you want to store it in a computer, you have to write it in this form. So what is this means? You move this dot all the way to the front, right? And then if you move it all the way to the front, you have to have 10 to the power 3 to get it back. So that's what it is right here. Okay, so this is usually you say exponential form, right? So this is actually normalized form. So this is what we're going to use actually. Floating point numbers are stored in a computer in 3 parts. The first significant bit, so what does this mean is what I'm talking about here is nothing but you will have 3 parts on your register, right? Okay, so this is your register right here, and the first part is plus or minus value, so you can represent this by 0 or 1, right? And the second part is a mantissa, which is we call this part is a mantissa, right? This is what the value is. This is what the value is. So you store that by zeros and ones and zeros and ones like that. So you will have a number of bits to do that. Okay, so these are a number of bits. So if you have 32-bit, well, you wisely divide that into some amount here and the rest here. If it is 64-bit, you focus, of course you can store much bigger values, right? Alright, so that's how you store things. And then yeah, of course I have to store this value right here, so that comes here, right? So that means what is number 3 is 1100. How do I know it is number 3 here? Well, this is 2 to the power 0, 2 to the power 1. So if you multiply these two together, I get 1, plus if I multiply these two together, this is 2 to the power 1 is 2, multiplied by 1 is 2, so this answer is 3, right? You see that? So that is how we store values in the computer, especially floating point number. You have all this to consider, right? Okay, so that's how you're storing things. But you're already aware in a computer you don't have much space, right? Okay, so these are the definitions. I'd like you to remember these. If you don't remember these, just go back to the one I was talking about and then just try to understand that, right? So the floating point number is expressed with a decimal exponential, right? So actually exponential notation is represent the floating number as a decimal fraction times the power of 10, right? Obviously that's what I was just talking about. And this is the form. You just having a dot in the front, and then you will have a full number, which is like this right here in the bottom, right? So what I'm saying is here it is the number. So this is what A is actually, right? So that is A, right? And 10 to the power another value here. This is N, right? So that's what they're saying. Okay. And it drops the decimal point from A is the significant or the fractional part of the mantissa. So that means this one has 3 names. Either you call it significant, you call it fractional part, or you call mantissa, right? So that is what it is. And this one right here is called exponential. Exponent, actually. Exponent, yes. So that's what you call that. Alright, so the normalized number exponential in exponential notation has a decimal point immediately proceeding to the first 0. So what I mean is, if it is like this, obviously you have to have this form right here. This is the normalized form, and 10 to the power minus 1. Why? The actually what you have to do is not multiply by 10, actually divide by 10, right? So this is actually a number, something look like this: 9200 divide by 10 will give you 0.092, right? So you can see division is moving the decimal point to this way. So this is the same way. If it is under the line, you can also write it like this, right? Okay, so that is that for significant digits, if you want to represent that. The one interesting point here is, how do I represent that in the register? Because you have a mantissa part here, and then you have an exponential part here. So this exponent is negative. In that case, how do I represent that? Well, you have to define a sign somehow in order to come up with this storage method on the registry. Okay, right. So all right, so this is the floating point numbers and how you represent floating points numbers in a register. Right, so you can already see there can be so many errors on this process, right? So we're going to look at the errors. Why the errors comes in? Well, if I don't have enough switches to represent this number, well, that is a problem, right? And also I have few pieces in my registry, right? And well, I'll move on, and then I'll talk about that in a minute. Right, so this is a precision. The precision is a number is the precision of a number is the number of significant digits that you have in it, right? Magnitude is a 10 to the power value, right? So these are the example of it. So if I have this number right here, right, the precision of this number is actually 4, right? And the magnitude is 7. So what this means is, okay, so this is the value. If I want to write this in a normalized version of it, I put the dot in the front right here. I don't want to worry about the front zeros here because it doesn't mean anything, right? But the rest it does. So in that case, if I have a value like this, I can put a dot right here. And then if you put the dot right here, anything behind this 4 doesn't mean anything. So in that case, the significant value in this case is only this 4, right? Only 4 digits that I can count from here. 1, 2, 3, 4. So that's the 4 I'm talking about. And then to the power, obviously I have right now my dot is here. So how many positions I move it up to here? So it is 1, 2, 3, 4, 5, 6, and 7. Right, so that means I had to multiply this by 10 to the power 7 in order to move this dot all the way here, right? So that is why the magnitude is 10. In this case right here, if I normalize it again, my dot has to come right into this position. So that means actually 10 to the power minus 1, which means I have to divide this by 10 in order to move it this way. So this is what it is, that you can see 9200 10 to the power minus 1. So what is the magnitude? Of course I have 4 there, right? So that will be the magnitude of 4, of course, when I'm representing this value, and you multiply that by 10 to the power minus 1. And so that is what the value represents here. Okay, right, so that is the precision of this value. It's going to be right. Okay, and then this is the absolute and the relative errors. So what is the absolute error and what is the relative error, and what is this means? Okay, So let's take some values and explore that so you can understand what is the concept behind it. Right, so let's say I have a very small significant the floating point storage, right? So let's say this part right here is 16, right? So this is a plus and minus like I said in my computer, and this is the 10 to the power whatever the value I'm going to store here, and this is my manticer, right? And then this is the exponent and plus or minus. Okay, so let's say I have a number which is 8.05557.864 like that, something like that. Right, so this is my number, right? I want to store it here. So the thing is, it is too big obviously, because 2 to the power 16 I can get the maximum value I can get is 65,536 as I remember. Okay, so this is a small number actually. 2 to the power 16 is this, I guess. Right, so in this case I have to round this up and come up with a form that I can store it here. So what is the best thing I can do is write this one like this, 8.55, instead of 7 I put it 6 there, so I'm rounding it up, and the rest is 0 after the point here. The zeros doesn't matter. This is 10 to the power 0 anyway, so I'm going to store it here with this value. Obviously I can store that one here without any problem, but this one you cannot, right? So in this case, this is the actual correct value you got, and your computer is not good enough to store that value, so I store it in this form, right? So in reality there are two different values, right? So it's 10 to the power 0, so these are zeros obviously, but here this number is now is going to be 8,556 instead of this whole big value there. Okay, so this is where the errors comes in play, and you can see now there's a significant difference between those two, right? Okay, so what you can do is subtract from one to the other, and so if I get the difference between these two, what I get is actually this is the correct answer and this is the result value, right? So if you subtract one from the other, you get something like negative 0.0002144. This is what you get. So this is actually, you take the absolute value of that, so that is just having these two lines. So the absolute value of this is going to be this value, right? So there's one more thing I had to point out, especially in absolute values, you get the truncation. Actually you just cut it off. If you cut it off from here without rounding, so that means I don't have 6 here, I will have 5 here. It will be a different value. But if you there are two ways. One is rounding it up, the other is truncate. So we're going to look at those things as well. If you do the truncation, that means you don't round it up with 5 to 6. It will be remain as 5. If you round, that means if you truncate, what will happen is you just leave the 5 here. If you round it up, of course the 5 will be converted to 6. Okay, right. Anyway, so this is what you get as the absolute error, and then the relative error means this is how much is related to the your correct answer, which means this one right here, right? So you put that there and multiply by 100. So in that case I get absolute error, which is 0.00002144. Absolute value of that, divide this by 0.85557.856 and multiply this by 100. This is your relative error. Okay, so this is the relative error, which is this one right here. and whatever I got it here is my absolute value. Okay, so you have a clear idea. So let's look at some examples. Okay, so we'll move to the examples here and see what this means. Suppose computer has a precision of 3, allowing only 3 digits in a significant and truncates. So what is truncates means you just chop it off, right? I will talk about that in the next few slides. So the next significant 3 digits means you can store a 3-digit number. No computer has such a limit, the precision, but limiting the precision of 3 simplifies our computations and still illustration the problem. So okay, so that means, yeah, actually the computer right now, in the beginning even you get 16-bit machine, and then it converted to 32 later on, now it's 64. So anyway, this one says, okay, you have very small machine that you can store only 3 digits numbers, right? Okay, so here it is. I'm multiplying 2 numbers here. So if you multiply these 2 numbers, this is what you get, right? So this is the value you get, and I want to store this. So if you want to store this value, first thing you do is you normalize this. How do you normalize this? You get this dot to somewhere which is you can find a real number instead of 0. So I mean bigger number, bigger than 0. So I can put this dot right here, and if I put the dot here, it is 81168 multiplied by 10 to the power 4 is my answer, right? So that is the actual answer. Okay, so then what you do, you're going to store this value. So if I store this value in my computer, I have some errors, right? Actual error I'm generating by doing this is equivalent to, this is my correct answer. You subtract your rounding up value. So this is the 3 digits, and then there's a truncation, means you cut off these 2 values. Just simply cut off. That's what I did. So then this is the value I get after cutoff, right? So this is the original value, this is the cut off value, the truncated. So then the answer is 6.18, right? When you round it up, I mean when you calculate this is what you get as the actual error. So that is what we call absolute error. So it's a huge error actually. 6.8 is a big error, right? Obviously if you have only 3-digit number registry, this is what going to happen. So the relative error is you divide that by the actual value. So when you divide that by the actual value, of course you can get some values look like this, and then you multiply by 100. So that's why you showing it as a percentage, right? So so yeah, if you get the relative error this much, that is also not good. That's what it says. So you should get a really small values will be okay, but if you get a significantly bigger error, it's not good, right? So but I believe you understand what is absolute and relative errors. Okay, so now we're going to look more. This is one what we call truncate a number, which means using this number right here. Okay, so if I want to truncate this, right, so what I do is I'm just cutting off from here. So let's say I just want only 2 values, 2 decimal places. So if you truncate this, actually you get 6.23. You just cut it off. You don't round it up. Round means you're adding 1 here, thinking about this value is greater than 5. So we'll talk about that as well. Right, so in this case your truncated value will be 6.23, right? So I just cut it off from here, and then your absolute I mean the correct value is this, your truncated value is this, so the error between those two is 0.009. And if you want to calculate the relative error of this, you divide this by the correct value and multiply by 100. So this is what you get. Okay, so this is what you get. Right, so that is how you calculate the relative and absolute with the truncate, right? Rounding error is the next one, which is also you can calculate the absolute error, but in this case simply what you do is you consider the number after the position that you want to round up. So let's say I want to round up things to dot 0.88 somewhere here, right? Okay, so there are two ways that you can round up. One is a round down, one is a round up, right? So if you do the round up or the round down, so round up means usually if this value right here, right now I have 68, that is greater than 50 or greater than 5, this number is greater than 5. So in that case, if you do the round up, what you do is you add 1 to this guy. So you ended up with 0.812. That is rounding up, right? So that is rounding up. So if I want to get round down, right? Round down means it's like the similar to truncate, right? Okay. If it is less than 5, actually, in that case you don't add anything here. But in this significant case, if it is 6 here, if that number is greater than 5, obviously you do have to add 1. So this is what the procedure, you go with the round, right? If it is not, if it is less than 5, we call it round down, right? So round up is the one which you have to go with, right? So this is what it is. That's you can go through this example and understand. I think it's simple enough. You don't need much more explanation. Okay, right? So so those are round errors. So you call it round errors. Round error is nothing but if you this one, whatever the value is, bigger than 5 or the 50 in this case, in that case you add 1 to here. If it is not, you don't, right? So that's what it's explaining here, round up and round down. Round downs occurs whenever the number here is less than 5. Round up occurs when this number is greater than 5, which is this one. In this case is this right here. Okay, and so this is the same thing I just explained to you in definition, so you don't have to memorize this. If you understand this, it's really enough. Okay, just try to understand rounding, right? So then overflow and underflow. So what are the overflows, right? Overflow means, well, I have this number right here, and suppose that you have a very small computer. In this case, I will have 16-bit machine to store an integer value, 16-bit. So what is the maximum number? Well, as I said before, so that's why I picked 16-bit actually. So the number I can do in my 16-bit is actually this, right? So this is equal to actual, the number of this is equal to nothing but 65,535. That's the maximum number I can store. Okay, so this means what? This means I have a 16-bit number machine. Actually, I'm taking it back. If it is just a unsigned signed number, this first digit right here will represent plus or minus. Okay, so in that case it's not going to be this number either. This is a very small number, because why? Well, this guy right here is representing your significant bit. That means your, is it a plus or minus? So that's what it's considering right here. That means 0 or 1. Depending on the 0 or 1, I know this is a number, negative or positive, right? So then I have two numbers to add here. When you add these two numbers, right, it will exceed this space that I have here to here, right? Okay, so how much is space that I'm talking about here? Let's say it is going to be 2 to the power 15 because I have plus or minus right here. So what I get actually 2 to the power 15 here, which is equivalent to I think it's 32,767. That is all I can do because there's a minus 1, otherwise it's be 68, right? You have minus 1 here obviously. So yeah, so this is the number I can store there, right? Okay, so this is the number I can store. Okay, and well, do I have space for that? No, unfortunately no. When you add these two numbers, it will exceed this number right here, right? So if you add these two together, obviously it is less than 65,000, so because of that you are not going beyond this line, but it will have some value at significant bit, which you get for 6, 8, 6 and 3. So only maximum number is 32,000. Now I have this. So if I convert this to binary, you will have extra 1 here. Okay, extra 1 here. So if it is a positive number, I already have 1, and then if I add another 1, this will become 0. So that is why you will get a negative number as your result. So this bit will be changed by the value. So when it is changed by the value, whatever the value you get from here to here will be this. So the answer, when you add these two numbers, will give it as a negative number. The reason for that is this value right here is overflowing your register, so it is getting more. You need the more space to store that value, but you have the more space, so it will write right here. But when you write it there, it will change its sign actually. So if you have the wrong sign, you get a wrong value. So this error we call overflow error, right? So that's what they're talking about here. And the overflow bit causing a loss of a rocket that took 10 years to make and $7 billion to develop in 1996. So what happened was actually they put all parts with a different size of registers in that hardware piece. But the software guy written the program for maybe 32-bit, maybe 16-bit, but you had 8-bit circuits. So what happened if you have 8-bit circuits and you written a program for 32-bit, right, or 16-bit? Well, obviously these kind of problems comes in because there are no way to check these things, right? Because it's hardware calculations, and the registry is the one which is storing it, so nothing but zeros and ones. So then, yeah, the calculation started wrong. 7 billions, and the 10 years is gone. Because of this reason. So this is an overflow issue, right? And the underflow is the same. In this case, you have really small numbers to store, and you don't have even if you use the space that you have, you unfortunately get zeros. For example, this one right here, right? So this is an underflow issue situation, and suppose the smallest floating number in a computer can express is 10 to the power minus 39, and you have something with 10 to the power minus 48. So that means you have a registry, let's say you don't have to go that far. Let's say I have only 3 digits and I have this much and 5 there to store. I want to store this number, but I have only 3-digit space here. So that means I can store only 0, 0 and 0. So this will represent and give you back 0 as your result. But actually there are some numbers here, some values that is actually happening. But this calculation never going to give you this value. It's always give you 0, right? So this is the underflow issue, which is you don't have your number is too small that you don't have space to store it right. So those are precise calculations that can happen, can issue some problems like that. Okay, so that is the issue that we are talking about here, right? Right, so let's move on to the other error types that we have, right? Okay, and this is an arithmetic error. In arithmetic error, especially when you're adding two numbers, right? So there are two numbers here. I'm going to add each other, and then when you add this, and the computer allows again only a few numbers to store. The same example I went through, right? In this case, yes, I will use this number and ignore this 95, right? So if you ignore this 95 and if you store only this part, right, obviously I have an error of 0.950 multiplied by 10 to the power minus 2 because I just kick this off. I consider these as zeros. Why I don't have enough space? So this is what I get when I normalize this value. This is what I get. This is a normalized form of storing this one in a 3-bit register in a machine, right? If I have a smaller machine. Well, if I store it like this, if I write it back, I actually writing 68,000. I mean, this is what I'm writing, right? Okay, so but is that not the case? Actually, I'm losing all these values because I cannot, by reversing this one, I never kind of generate this because this part is already lost. So that addition, if you do the additions like that, and you might end up with losing some values. So that is also an error. So these are pretty common in computers. If you come to large numbers, if you don't address it right, if you address only the size of registry thing, unfortunately you will face this problem. Okay, so that's that. And then the propagation error is coming on the loop. Let's say I have a loop and doing the same thing on and on, right? So when I'm doing something on and on, it will increase the problem, I mean the error, and it adapt to the errors, so on. So I mean continuously. So what this means is one method is updating a time can be lead a serious accumulation of round-off errors. So for example, I get some number here, 8 point, let's say 8.5678, something like that, and I'm multiplying this by what I'm doing is I'm multiplying this by some number, right? Or I'm using this number to calculate something, right? And then so this is too big, so when I want to calculate this, I'm just consider this one as 8.6 and I calculate a value. Maybe I'm multiplying it by another 15 or something like that. Okay, so then again I will get a bigger number, right? I get a bigger number here, something which is giving you by that. So I don't know exact value, or let's say I'm assuming this is the value. Again, I'm going to round this off again to the 8.6, right? Let's say this one is 8 right here. So in that case, it is 8.9. There's a significant error here. There's a significant error here, and so on. Each time when you're having some values, you round it off to 1-bit value. So that means all the errors I get here, all the errors I get here, and all the errors I get from each time accumulate together. So that is a propagation error. So each time when you do something, and if you round it up like that on and on, that will give you a propagation error, right? So that will be a loop. Actually, when you're doing it in a loop, obviously these kind of things can happen, right? So okay, so this is what the propagation error is repeatedly execute the same thing on, and it will create some errors in it. Okay, so I hope you understand that. You don't need much explanation on it, right? Okay, So violation of numeric properties. Oh, this is the interesting one, which is sometimes when you multiply two numbers and divide it by one number, is not actually equal if you divide two numbers and multiply with another, right? So usually these two has to have the same output. These two has to have the same output, right? What I'm doing here is first I'm dividing this and multiply by one value. This time I'm multiplying this and divide by one value. It's the same value, I'm going to divide it, but the order of calculation is different. If you do this in a three significant digit machine, you're obviously going to get two different values, right? So this is an error, which is a violation of numeric properties. That is something can happen in smaller size devices. However, in mathematics, there are two properties on this case. One is the associative property, which means it doesn't matter the order you add numbers together or you multiply numbers together. The order doesn't matter, right? And there's another one called a distributive property, which you can multiply either adding these two and multiply with this, or you can multiply first and then add. So these are distributive properties and associative properties. So I hope you will, I'm expecting you to know what is associative property and what is distributive property in math. So keep asterisk on these two. It's better you know those things. Obviously, the violation of numeric property, I'm expecting you to know these things. Okay, right? Okay. There's nothing much to talk about here. This is one kind of a numeric violation of the property. Whenever it is doing the order differently, you get these errors. This is very often happens even in your calculator. Sometimes these things happens, right? Okay, right. So that is that, and okay. So the comparison of floating point numbers. How do I really going to compare two floating point numbers? So this is a very important rule, especially for the programmers out there. Usually when you're having two floating point numbers, like for example 5.658 and I'm going to compare this with another number. So if I say equals 5.75879, these two numbers are never going to be equal. Why? Obviously you know that, right? So this one has some additional value here, this one don't, right? So whenever you have something to compare like this, it is not a good way to do this, right? Especially when it comes to the floating point numbers. So what you should do when you're having a floating point numbers, how you should compare these two is get the difference between those two numbers, right? Get the difference, subtract this value. So get the difference of this and get the absolute difference. So that means I get only the absolute value of this. Right, so you get the absolute value and see what is the difference between those two. If it is less than a threshold value, which is we call C, I say, let's say this is 0.00005 or something like this. This is your threshold, right? And that means, okay, if it is less than this, if it is greater than this, you proceed, otherwise you don't. So instead of equals on the floating point numbers, it's much better you subtract these two and get the difference. If that difference is really small, you proceed, otherwise you don't, right? So this is what the threshold means, right? So this is what threshold, I think threshold value, right? So that is what the threshold value means. Okay, so that is very important, especially when you're coming to the floating point numbers. How are you going to compare this? right? If this value is really small, you consider these are equal, otherwise you don't, right? So this is something you should keep it in mind, especially when it comes to the floating points. Okay, all right. So right, and then the truncation error. The truncation error is an error occurs when when truncated or finite sum used by approximation of the value. So for example, this is the Euler equation. I think you remember this is an irrational number, and we talked about this a little earlier in the semester, right? So so this is the e exponent value of x. So this is what you get from that. Okay, so this is something. Actually, when you divide something by this, it is a significantly very small number here, right? Okay, and when you calculating that, it's give you the approximation value like this, right? This value barely is equivalent to 1 over 21. Whenever you take the value of factorial 1 over 21, that is really small number, right? So you cut off some values because it's too small, and this is truncation issue comes in. And when it comes to that, with really big numbers as the dividend, you get some significant errors like this, right? Okay, so this causes the truncation error. This is nothing but when you're adding series of numbers by rounding up or let it go. This is what happens. Okay, so these are actually happening in electronic devices you have. This is not going to give you the exact number because of this. So even your exponent values are not always accurate. Okay, keep that in mind. Exponent values in mathematics is not the same as exponent value in the electronics. So the electronics cannot handle it for that far, right? Okay, right. So that's what it's showing here. Right. So yeah, so that is all the errors I'm planning to talk about in this lecture. Yes, you're going to have a quiz on. I will announce that anyway. Uh, for the rest 2 weeks, we will have quizzes. So that will cover all the quizzes we can do. We missed one because we closed down on 1 week, and that will kick us back, right? So, but the last two quizzes we're going to have on the rest of the Fridays. So we'll talk about that. Right, so this is the errors, and then we'll talk about functions, and yeah, so then the next quiz will cover all these lessons. So make sure you understand these things. Okay, right, I'll see you in the next lecture.